I do have a Chris Heil story that I think I wanted to start with. I was debating whether to do it at the end or not, but I thought that in case I run long, I don't want to do that, but in case that happens, I want to get it in. But I was there at the beginning. Chris and I, most of you probably know that Chris and I were graduate students together here at Maryland. In the 80s, we became students of John's at about the same time. And John set us to reading the sort of literature that existed at the time on wavelets. And at one point it was suggested we write a paper together. And that was published in Siam Review, and Oli, I think, mentioned that paper and praised it for its or how well written it was. And I concur with that, okay, not because of my contributions, but because of Chris's. And also, you know, we've heard many people talk about what a excellent expositor Chris is, and excellent writer, and I completely concur with that. But I thought I would lift the hood a little bit and give you an insight into how the writing process worked. Yeah, yeah. Well, so the way we did the paper is we would each write our sections independently and then join them together, and then we'd each take a run at editing the result. And when Chris would do the editing, I would get back the copy, and I'd see written in the margin next to something I had written, "This is worded funny," and so I'm not like William F. Buckley or anything. So I don't. I'm not a great writer, but I try to be clear. So I said, "What's wrong with it?" And he says, "I don't know. It's just weird." So all right. So I would change it. I'd reorder things, and it improved, I would say, in my own mind. And I'd show it to him again, and he'd say, "Well, it's a little bit better, but I think we need to move on." So I would say that given Chris's tremendous output in terms of exposition and in terms of research, that if Chris tells you that something is worded funny, then you should believe him. Yeah. And I actually think that Chris's books will be, I mean, they're really great, and that those will remain in print, in my opinion, for decades. So you can check me in 30 years to see if I'm right or wrong, but they really are superb. Also, if you read that Siam Review paper and you run across something that is worded funny, then that's evidently a part that I wrote. So we'll see what he says about these slides. So the work that I'm going to talk about is joint with Bjarte Ram, who was a student of Yuri Libarski, and we worked together on this stuff quite a while ago. And the content, the mathematical content of the talk will be based on basically on this paper. Okay, so it's my most recent, so it's 2000, but it's my most recent collaboration with Chris. So this was a paper that Charlie, Chris, and I wrote, and what I want to do is take the result in here and generalize it in I think, a kind of interesting way. Okay.
I just want to point out that my name is on this paper because I gave Dave a reference. He did everything else.
So you're trying to run away. Okay. Yeah, so this paper is worded funny, I'm sure. Anyway, yeah, and there was a sort of a companion to this paper, basically a commentary on it in the same issue that clarified some things, I think, in a nice way. So I want to acknowledge that work by Sipe. Yeah. So let's see. So let's get into it. So the result we prove is called the local three squares theorem, and it says the following. Okay, suppose I have a function defined on a large square, okay, of side 2r, and what I want to do is compute the averages of this function over three smaller squares. So I'm basically taking the average of this function over all shifts of these three smaller squares that are completely contained inside of the larger square. So there's no thinking about what f is doing outside of the square. We're basically convolving, but we're not padding by zeros. We're not assuming it's periodic, nothing like that. We're just completely inside this larger square. So obviously these are restricted convolutions. And so the theorem is down here, and it's holds in d dimensions. But the actual three squares theorem says that such a function is completely determined by these local averages if and only if R1, R2, and R3 are pairwise or rationally related. And so here's the statement of that. It holds in higher dimensions as well. Sorry? Just because, I mean, if you go down here, right? So I like to use the symmetric interval down here. That's all. Yeah. Yeah, I went back and forth on that, and I thought this was worded slightly less funny than otherwise. But sorry. Correct. Yes. Yeah. And let's see. So yeah, I wanted to take a minute to just give some context on this problem. The theorem a version of this was first proved by Bernstein and Taylor in the 70s. Okay, Laird came up with a nice elementary proof that is similar to what we're going to do. But they were studying at the time local Pompeiu problems. And the version of the Pompeiu problem that they looked at was the following. Start with a family of compact subsets of R2 and look at essentially the convolution of a continuous function with the characteristic function of P, and ask yourself, is F completely determined by that convolution? Are there non-zero solutions? And so this was some work done in the 80s by these folks, and their point of view was to try to find a way to reconstruct F. So if these compact sets are such that these convolutions being zero imply that F is zero, so if F is completely determined, can you find explicit formulas for the reconstruction? Now, these kind of problems they show up everywhere they're very important in mathematics and harmonic analysis. They touch on the ideal structure of Banach algebras. They are related to spectral synthesis. Also, the Fugleda conjecture there's papers called the Fugleda conjecture and Pompeiu problems. And also, connecting with something that John mentioned yesterday afternoon, basically the three squares theorem is approximating a function from inside of its own support, which is something John mentioned as a goal. But the goal of these folks was to find explicit solutions, which led them to look at analytic Bézout identities. Okay, so here the mu j's, as considered as compactly supported distributions, are characteristic functions of these sets P. And if this has a solution, then F is completely determined by these convolutions. And there's more names associated to this, including Hormander, who characterized when such solutions exist. And of course, the equivalent problem, when you take the inverse Fourier transform, is resolving a delta, again, from convolvers, which are characteristic functions of sets. Okay, and this introduces a signal processing and image processing element to the work. Okay, and more names in the 90s and a little bit into the 2000s as well. So what I'd like to do in the talk is give a proof of the local three squares theorem that we essentially the same as what we did in the paper, and then generalize it and show how there are similarities to the approach. So first of all, one little notational point, okay, I'll use capital F for functions in L2 of an interval, and the corresponding Fourier transform will be the lowercase letter. Okay, so it's sufficient to look at the d equals 1 case. So what does it look like on the real line? And to do that, to prove that, it relies on results on completeness and interpolation properties for certain collections of exponentials or certain sampling sets in L2 of minus r to r or in the corresponding Paley-Wiener space. And so the sets we look at are unions of lattices in the real line. So what do I mean by that? I mean, so I have m positive numbers. R is the sum of these numbers. I look at these lattices. So they have density 2 times rk. And then, I take the union of these lattices. So clearly, right, depending on what the r's are, you can have a point in multiple lattices. So we assign a multiplicity to each of these points. Okay. So the corresponding collection of exponentials looks like this. Okay. So the lambdas come from the union of the sets, and the j, the multiplicity determines the powers of t that are on here. So we ask questions about completeness and about uniqueness from samples. So the samples on lambda mean the samples at the points lambda and also samples of their derivatives. Okay, so is it complete, exact, what? So here we go. So the some sort of sum of what is known about such sets. I mean, they're very simple they're very simple sets, so a lot is known about these properties, and I've summarized some of the information here. If all of the r's are rationally related, then you have a respaces. Okay, so we're not interested in that case, but everything is nice if everybody's rationally related. If one pair at least is irrationally related, then the following three things are true along with other things. Okay, first of all, you don't have a respaces, you don't have a Schauder basis, but you do have an exact system, okay, meaning it's complete and minimal. Okay, so equivalently, a function in this space is determined by these samples, and interpolating functions exist. Now, it's well known that the sequence bi-orthogonal to an exact system in a Hilbert space is not necessarily complete. It's a kind of a strange result, but it's true. And Chris has many examples of this in his book. But in the case of exponentials, Young has shown that they are complete. Okay, the sequence bi-orthogonal to these exponentials is complete. And Sipes' observation in the paper that I mentioned is not only is it complete, but it's over-complete. So, and let me say what I mean by that. So if we look at the interpolating functions, now we're getting into the proof a little. We're going to make the assumption of the theorem. So every pair is irrationally related. So what that means is that all points have multiplicity 1 except for 0, which has multiplicity m. So in interpolating, we interpolate at the points on lambda, and we interpolate the point and the first m minus 1 derivatives on the at the origin. So it's easy to write down the interpolating functions. They look like this. So we have a generating function, just a product of signs. And we look at this collection of functions, and these are the interpolating functions, which are complete. And we can say a little bit more than that, okay? This first bunch of functions here, they interpolate the derivatives at the origin, okay? The remaining functions interpolate just to order 1 on lambda, okay? And it turns out that these functions are excess. You don't need these. The higher order interpolators are not necessary, that these functions by themselves are sufficient. Okay, these form a complete set in the Paley-Wiener space. So now it's like falling off a log to finish the proof. If I take the inverse Fourier transform of these guys, I get this collection of functions, which is complete in L2 of minus R to R. Okay, and to finish everything up, I take M to be D plus 1, and I take D-fold tensor products of those functions on the previous slide. And you can always factor out one of these characteristic functions, and you come up with a complete set like this. And that is sufficient to prove the theorem. Okay. All right. So what Bjarte and I wanted to do is generalize this, getting away from squares now and going to parallelograms. What if you just make that simple change from squares to parallelograms? So this is what the theorem looks like. We have 3 parallelograms, and what replaces the large square of side 2R is the algebraic sum of these parallelograms. Okay, so the edges of this polygon correspond to the edges of the parallelograms. So in theory, this is a 12-gon because there's 6 edges, but you can see a couple of them are parallel. This one and this one look parallel. So are these. So end up with an octagon. Okay. And so the statement of the theorem is the following: if we have 3 parallelograms, M is the sum of the parallelograms, is a function in L2 of M, uniquely determined by these restricted convolutions. So these would be shifts of each of the parallelograms completely contained inside the larger one. Okay. And what's the criterion? Okay, so I left you in suspense on that. Couldn't fit it here anyway. Yeah, I want to give you the idea of how the proof goes in order to sort of motivate where that comes from. So how would you prove this? Well, what did we do before? We came up with a complete set of exponentials for functions band limited to this polygon. Okay, and so does there exist such a thing? Well, fortunately, it turns out that Lubarsky and Rashkovsky studied this very problem themselves, and they came up with an exact system of exponentials for L2 of a symmetric polygon like this. Okay, and it's more than just an exact system. It's actually what's called a respaces from subspaces. So it's almost a respaces. You have to sum in bunches, kind of like information packets that Oli was talking about. But anyway, our interest is mostly in the completeness. So what is that set that they discovered? Well, it's easy to construct. You take the 3 parallelograms, look at the vectors that correspond to the sides of the parallelograms, and you define this collection of hyperplanes. So for each direction, okay, each j, and each integer n, you make a line that is perpendicular to bj, so cj is perpendicular, and which is separated by the reciprocal of the length of this b. So I think that's not too hard to understand, but I wanted to draw some pictures. I'm not good at this, so these take me hours to do, even though I'm going to flash through them. Just want to let everybody know that. But so yeah, this is our octagon. Okay, I've colored the parts of the sides corresponding to the edges of the 3 parallelograms that I drew. Okay, so I got red, blue, green, orange. I think that's purple and pink. Okay, so what would be the frequency set for a collection of exponentials that is exact for L2 of M? Well, what I say before. So let's take this side here. Okay, I'm going to draw a collection of lines perpendicular to this red vector, and whose separation is the reciprocal of the length. So that first bunch of lines might look like that. Okay, so the scale is up to your imagination to get it correct. But always one of the lines is going to pass through the origin. Okay, so that's for this red edge here. Now this edge, okay, well, there's two that are parallel. Okay, so this is one edge, but they're two corresponding to two sides of parallelograms. So we have two collections of lines, okay, which are, again, perpendicular and separated by the reciprocal of these lengths. So you'll get two lines like that, sets of lines like this, okay? And I'm going to draw in the third one. Okay, really there's one, two, there's three more, okay, sets of parallel lines, but the picture is enough of a mess as it is. So I'm going to just do the orange one here, okay? So we have these lines, and notice that in each set of lines, one of them passes through the origin. So there are many lines passing through this point. Okay, and let me get rid of the parallelogram. So this is in the frequency domain. I should have said that. So I have this ghost of the parallelogram. I'm sorry, of the octagon, just to show where things come from. So this is the collection we're looking at. Now, Lubarsky looked at the set of all intersections of all of these lines, okay, and showed that this gives us the exact system that we're looking for. Now, what he did is he shifted each of these collections of lines a little bit so that you never got more than two lines intersecting at a single point, okay? But with our application, you definitely do not want to do that, okay? So the problem comes in when you have a triple point, like that, or maybe like that, something like this. So what's the criteria for the result of the theorem to fail? That is, you can have a non-zero solution to these convolution equations. Well, what has to happen, it turns out, okay, and actually when you see this, you can, it's not that hard to realize, is that if I have a triple point, okay, and again, there are more lines that should be here that I didn't draw, but it could be more than three intersecting. So if more than 2 points intersect, then if the directions corresponding to these three lines, or the sides of the parallelograms corresponding to these three directions, come from distinct parallelograms, then it fails. Then that's the criterion. Okay. So in this case, if you go back, so I went back, I'm not going to bother doing it, but you look at the three parallelograms I drew kind of at random. Oh, what the heck? There we go. So if you look here, right, if the red, the blue, and the orange line that we're intersecting there came from distinct sides, okay, so maybe one came from that direction, and that direction, then or distinct parallelograms, then the theorem fails. Okay, so what if you do go back? No one, I don't know why you would. This is okay, right? Two of these come from the same parallelogram, so this is allowed. But go down here, whoops, okay, got red, green, and orange. These three directions come from distinct parallelograms, so the picture I drew is doesn't work, okay? There are non-zero solutions. And it turns out this is the necessary and sufficient condition to get the three squares theorem to work for parallelograms. Now you can guess clearly that this is sort of a geometric, criteria here, but obviously there's an algebraic one that you can put in, and that is the thing that I did not want to put up right away, and that is this. Okay. Okay. So here's the what we want, that f is uniquely determined by these local averages. This is this fact that for every choice of a side from M sub I, you never get three lines meeting. Okay, so the intersection of these three lines is always empty, and so I'm not. I have a little bit of time. So the I should point out that that all bets are off when you're talking about lines through the origin. Okay, it's only if you have a triple point that's away from the origin. So clearly, this is a triple point, right? We have two lines in the same direction, and so we have 1, 2, 3 lines meeting together. But that's legit. That's okay. It's not going to hurt anything. So that's why it's non-zero integers here. And the algebraic condition is the following. So for every such choice of side, so BKI, if two of them are parallel, then the lengths have to be irrationally related. So that makes it a generalization of 3 squares. And if not, then these 3 determinants are linearly independent over Q take away 0. So that is, there's a non-zero, okay, so linearly dependent would mean there's non-zero rational numbers that whose combination will give us 0 here. Okay, so let's see. So what's the idea of the proof? Okay, one of the goals here is that I want to demonstrate that, you know, the proof of the 3 squares theorem was basically a one-dimensional result. You just do tensor products and you get it in higher dimensions. This one is also essentially a one-dimensional result, but it's not taking tensor products. So the main point is this lemma here that says, suppose I have a function band limited to this octagon, let's say, and that B or C of the theorem holds, then if F vanishes on these lines, okay, so this is much easier to prove than Lubarsky and Rashkovsky's result, but if F vanishes on all of these lines, including higher order vanishing where you have double lines, so you need the function to vanish here and also its directional derivatives in a perpendicular direction vanishing, then then F is identically 0. Okay, so the goal of the proof will be to take each line and argue separately that if these convolutions are 0, then F must vanish on that line. Okay, and here's where the reduction of dimension comes in. Okay, so let's say we're in our minds we're fixing this line. We want to look at it. Well, it's this line through the origin sort of displaced by a certain amount. Okay, so what I want is a function of one variable whose Fourier transform is little f, right? The Fourier transform of the whole function restricted to that line. And how do you do that? Well, I need to shift it and then project it down. So so I just basically dropped this thing down and I drew a picture sort of like that. Okay, so so this line is the red line through the origin. I project down, and what I get is a function that's supported on this interval, which is a sum of, and the length of this interval is a sum of these numbers here. Okay, so each of these f's is in is in L2 of an interval where this interval is formed by these, you know, projections down onto the line we're interested in, onto the line in direction j. Okay, and I added all 6 because one of these is 0. Okay, so what we have then is, this is the last thing that I will say. If I look at this line, okay, what do I have? I look at the points, right, of the other lines intersecting this one. And that is a union of shifted lattices, okay? Everything I said before about shifted lattices works when you shift each of the lattices, okay? Not necessarily off of each other, but just shifted. So, so then we just exploit results that we know about complete systems of, you know, convolutions on you know, that correspond to unions of shifted lattices. So it's basically the same argument, okay, except you project down to one dimension along each one of these lines. Okay, so that is let's see, there we go. So that's this last thing here. Okay, a lot is contained in that, but you can exploit the results. That gets the sufficiency of our condition, and necessity, like I said, is not too bad once you see what's going on. So thank you very much. Whoops. Thank you very much, and happy birthday, Chris.